We've been discussing the rates of reactions in a very phenomenological manner, and in this video I'd like to talk about some of the energetic aspects and how those affect reaction rates. So our goal for this lesson is to determine energies necessary to initiate a chemical reaction. Now I'll remind you that we came up with a reaction energy diagram a couple of modules ago that may have looked something like this for an exothermic reaction. We start with reactants on the left. They go up over a hill and down to products, with the enthalpy difference being the difference between the level at which the reactants is from the products. Now, we mentioned briefly that the height of that barrier, that is between the reactant energy and the transition state energy, was something called the activation energy, and that was related somehow to the speed of the reaction. Let's fill this out a little bit more. Well, first of all, when we talked about equilibrium, the equilibrium position of a reaction really is a function in part of the relative enthalpies of the reactants and products. In other words, delta H is what determines, in essence, the equilibrium constant for a given reaction. It has nothing to do with the height of the barrier between reactants and products. That just affects how fast they get there. So the rate of a reaction is going to be related to the height of that activation barrier. And our intuition tells us, and indeed our experience in the lab tells us, that the higher that barrier is, the slower the reaction. So if we have a small barrier, we'll have a very rapid reaction. If we have a high barrier, we'll have a very slow reaction. Now, you'll notice that the horizontal axis there is labeled reaction coordinate. Let's take a moment to talk about that. What is the reaction coordinate? Well, let's suppose that I have a reaction that looks something like this. It's the dissociation of ozone into a diatomic oxygen and an oxygen atom. In this case, it'd be pretty easy to figure out what the reaction coordinate is. It's simply going to be the distance of the bond that's breaking. So when you break a bond, that's the reaction coordinate. Is it going to be as simple as this for all reactions? Well, probably not. Let's consider a little bit different reaction. This is one where we have a chlorine atom reacting with hydrogen bromide, and the chlorine basically strips the hydrogen off of the hydrogen bromide, leaving a bromine atom. All right, so we've got a few things going on here. We've got a new bond being made between the chlorine and the hydrogen. We've got an old bond being broken between the hydrogen and the bromine. So now our reaction coordinate is really some kind of combination of the distances between hydrogen and chlorine and the hydrogen and bromine. So it's not quite as straightforward. I would say that in general, the reaction path, the path that a reaction takes, involves changes in a number of different bond lengths and angles. So if it's a more complicated molecule, there could be many different coordinates that are contributing to that. So I want you to think of the reaction path as simply, the path that you might take on a trip. For example, if you're driving in the mountains, the reaction path is your path along the road. But if you were to specify exactly, how much you turned right and how much you turned left and how far you went each time you in between those turns, you'd have to give a very detailed and complicated account of how you took that path through the mountains. And the same is true for molecules going through a reaction. I'll then define this activation energy, which we've drawn abstractly on the reaction energy diagram, as simply the minimum energy that's along the path that it takes needed to initiate a reaction. So in other words, we're going to have to get over some kind of energy barrier, and we're going to be following some reaction path along this reaction coordinate. And the minimum energy along that path is the one that's going to be needed in order to initiate this reaction. So how is this connected to the rate constant? All right, remember when we set up these rate laws, we found that if we have two reactants, A and B, going to products, that the rate is going to be somehow proportional to the concentrations of those reactants times the rate constant. What is that rate constant? Well, this was something that people studied for many years, and they found that, in fact, as temperature increased, the rate constant increased, and as temperature got very low, the rate constant went very low. And ultimately, through a lot of experiments to measure how the reaction rate changed as a function of temperature, ultimately we ended up with this equation, now called the Arrhenius equation. Same Arrhenius who dealt with acids and bases, by the way. That says that the rate constant as a function of temperature is this interesting combination of the activation energy and the temperature. So it's equal to a constant A times the natural base E raised to negative activation energy divided by RT. R in this case is the gas constant. It's the old constant we found with the ideal gas law. And this A is a collision factor. It's basically the frequency of effective collisions that go on in a reaction rate. So what does this function look like? Well, this is what it looks like. And we can see that as T gets very small, K goes to 0. Now, why would that be? Okay, when T is very small, then 1 over T is going to infinity. And if I raise something to the negative infinity, it's like something to the negative 100th power would be a very small number. Something to the negative infinity would be even smaller. In fact, it goes to 0. So we can understand that end. What about at very high temperatures? As temperature gets larger, 1 over T gets very small. And if we have something like e to the 0 power, that would just be 1. So that means that in that limit, K is going to approach the value of this prefactor A. So we can understand the two limits. The shape of the curve in between is basically an artifact of this particular functional form. So how can we use this to get information that we need? For example, how do we measure this activation energy? It's not an easy thing to measure because the transition state is a transitory state. It doesn't hang around for a long time, so it's not like it's hanging out there and we can just measure that energy difference. No, we have to infer it from other kinds of data. So the way we do this is we measure the rate constant at different temperatures. So I'm showing you some sample data here. Now, there's a lot of stuff on this slide, and what I really want to simply impress you with is that you can measure this information. You can take the temperature, you can measure the rate constant, which is the second column in the data table. You can then convert the temperature to 1 over T, and you convert the rate constant to log of K. And when you do that and take the Arrhenius equation, you can rewrite the Arrhenius equation as it's done sort of up and to the right of the table as log of the rate constant is equal to log of that prefactor A minus the activation energy divided by RT. So this really has the form of a log A minus EA over R times 1 over T. It's really got the form of a linear equation. In this linear equation, we've got B is this intercept, which is log of A, and the slope is e sub A over R, so that's going to be the slope of the line. So here I've shown a graph of those 3 points that we've taken, the best fit line that goes through them, and now when I do the analysis, the statistical analysis of this line, I would get an equation that looks like y equals 41.69 minus 15,524 times x. So I can interpret the first number as the intercept, so that's going to tell me something about the prefactor A. The second number is going to tell me about the activation energy. So if I multiply that number by R, and in this case we're using R is equal to 8.314 joules per mole Kelvin, what we'll find is that the activation energy for this particular reaction is about 129 kilojoules per mole. So this is how you would use different temperature data to indicate what the activation energy is. It's actually a very clever experiment and tells us something very useful about these reactions.